Hello friends, today's topic is learning with hidden data. Many real world problems have hidden variables or latent variables which are not visible in the data that are variable for learning. Latent variables can dramatically reduce the number of parameters required to specify a Bayes network. For example, medical records often include the observed symptoms, the treatment applied, and perhaps the outcome of the treatment, but they seldom contain a direct observation of the disease itself. One might ask, if the disease is not observed, so why not construct a model without it? So there are three symptoms: smoking, diet, and exercise. If you smoking, then the symptom is heart disease. Diet, if you have not taken proper diet, then it's a heart disease. If you are not proper exercise, then it is a heart disease. Symptom 1, symptom 2, and symptom 3. And this is a smoking, diet, exercise. If you have smoking, then symptom 3, maybe symptom 2, maybe symptom 1. If you have not getting taken proper taking proper diet, then it should be symptom 1, symptom 2, symptom 3, and then exercise, so on. Okay. So figure A, a simple diagnostic network for heart disease, which is assumed to be a hidden variable. Each variable has three possible values and is labeled with the number of independent parameters in its conditional distribution. The total number is 78. Okay. In figure 2, figure B, the equivalent network with heart disease removed, not that the symptom variables are no longer conditionally independent given their parents. The network requires 708 parameters. Assume that each variable has three possible values. Example, none, moderate, and severe. Removing the hidden variable from the network in figure A yields the network in figure B. The total number of parameters increases from 78 to 708. The hidden variables are important, but they do complicate the learning problem. For this, we use an algorithm called expectation maximization, or EM algorithm, that solves this problem in a very general way. The EM, what is EM algorithm? In many applications, the data we have is missing. Critical information is called the hidden data. The basic idea of EM is to pretend that we know the parameters of the model and then to infer the probability that each data point belongs to each component. Essentially, we are completing the data by inferring probability distribution over the hidden variables, which component each data point belongs to based on the current model. For the mixture of Gaussian, we initialize the mixture model parameters arbitrarily and then iterate the following two steps. First is E steps. Compute the probabilities Pij, probability of ij equals to P, C equals to I, given that Xj, the probability that datum Xj was generated by component I. By Bayes rule, we have probability of Ij alpha P Xj, given that C equals to I into probability C equals to I. The term Pxj, given that C equals to I, is just the probability at Xj of the ith Gaussian, and the term P equals to I is just the weight parameter for the ith Gaussian. So define the Pi equals to summation Pj into Pij. M steps, compute the new mean, covariance, and component weight as follows: mu I summation j Pij into xj given that Pi summation I summation j Pij xj given that Pi omega I implication Pi. The E steps or expectation step can be viewed as computing the expected values Pij of the hidden indicator variables Zij, where Zij is 1 if datum xj was generated by the ith component and 0 otherwise. The M step or maximization step find the new values of the parameters that maximize the long likelihood of the data given the expected values of the hidden indicator variables of the hidden indicator variables. Thank you.